Well, good afternoon. It's a pleasure to be here. So I'm somebody who works on the detection and characterization of exoplanets, planets around other stars. And this talk is a really nice opportunity for me to spend a little bit of time telling you about that, but also thinking about exactly what it is we're looking for, especially in the context of looking for planets that might harbor life and how we might go about finding signs of life on those planets. By the way, can I have a sort of 5-minute, you're close to the end, notice. Okay, so I use this title slide because for me, everything that we're doing in this field is about putting the Earth and the solar system in context. And in that sense, I personally am not necessarily interested in planets that harbor life more than planets that don't harbor life. I'm interested in the full diversity of planetary systems, but there is an argument for focusing on those that might harbor life as a way of targeting our efforts. And of course, of understanding how frequently life arises in the universe and where the nearest, for example, life-bearing planet might be located. So I'm going to start with some very back to basics reminders about, in the solar system, so our theories about how planets form initially were based exclusively on observations of the solar system planets, and you already have quite a lot of information. So a number of rocky planets in the inner parts of the solar system, a number of gaseous giant planets in the outer parts. Almost all of the mass is in the sun. 98.5% of the mass in the solar system is in the sun. Almost all of the angular momentum is in the planets, and that tells you something about how they formed. They also all orbit in nearly circular orbits in a plane, and as you move further and further out, you start to also realize that there is an outer component to the solar system, which is a reservoir of comets. So in the inner regions of the solar system, you have also a reservoir of asteroids between the orbits of Mars and Jupiter, and then in the outer parts, you have a reservoirs of comets, some of which occasionally get kicked into the inner parts of the solar system. And any theory of planet formation has to explain all of these properties. But ideally, we wanted to be able to predict the full diversity of planetary systems that we find. We'll hear a lot more about planet formation in the rest of this talk, so I'm just going to very briefly give a simple outline of the theory that was really developed in the 18th century, but some broad aspects of which remain correct to this day. So stars are thought to form as the result of the gravitational collapse of a cloud of molecular gas and dust. And in order for this collapse to happen, a disk needs to be formed so that the material can exchange angular momentum. And some material can fall in, carrying mass inwards, whereas some small fraction of the material carries angular momentum outwards. And in this disk is where the planets will form, and they will themselves form under the impact of, because their own gravity enables them to accrete material within the disk around the location of their orbits. And once the star turns on at the center, then you start to evaporate the material in the disk, leaving behind a planetary system. And the reason I've just given you this outline is because planetary system formation is a byproduct of star formation, so that immediately leads to the notion that every star is likely to host some kind of planetary system, and therefore that planetary systems would be very common in our galaxy and in the universe as a whole. And if you look at this, this is a very simple, it's actually a drawing rather than a collection of data assembled electronically, but it's a drawing made by astronomers at Lund Observatory showing every star that's visible to the naked eye in the sky and showing the plane of the galaxy here in the center. There's about 100 billion stars in the Milky Way, and each and every one of them is a potential host of a planetary system. And there's about 100 billion galaxies in the universe. So that makes a lot of potential planetary systems for us to find. And in the 1990s, we started to be able to image at high resolution in the infrared regions where stars are actively forming. So this is the Orion Nebula. And in these regions, particularly at the edges of the regions that have been cleared out by massive stars, where the material has been compressed by shock waves, we see little so-called proplids, which are essentially a little bubble of denser material around a star that's in the process of forming. And in these proplids, we actually see protoplanetary disks, which are actively forming planets, presumably. So this is just a zoom of this disk, which is seen in silhouette on the background of bright nebula emission. And you can see a disk. Now, this is several thousand astronomical units across, so we're looking at very large scales. But shortly after the first images like this were obtained, the first exoplanets were discovered. And so how would you go about finding an exoplanet? Well, one way of doing this would be to look for it directly, so to attempt to take an image of the exoplanet as it lies very near its host star on the sky. This is an image of an A star taken by the Gemini telescope, and Gemini is an 8-meter telescope, and at the distance of this star, 1 arcsecond corresponds to about 40 astronomical units. Now, this image is remarkably sharp, and this was achieved by using what was at the time very advanced adaptive optics systems. And you can also model in detail the point spread function, so that is the way in which the light of the star is distributed by the optics of the telescope. And if you subtract off the light from the star and you zoom in to the little square here, then you get this. So this is actually a 3-color image that's been made by summing 3 images taken at slightly different times in the same night. During that time, the sky rotates above the telescope, and all the imperfections which are caused by the optics of the telescope will move, but the planets, so here the images have been derotated, so the planets, any planets remain in the same place. So you can see here this mess here, which is the residuals of subtracting the light from the star, and all the 3 different colors don't line up, but there are 3 spots which do line up. And this system was confirmed as a bona fide planetary system around an A star after several years of following the system and also checking that the planets rotate around the star, and that as the star moves across the sky, the planets move with it, so they're not background objects. So this is a scaled up version of the solar system, if you like. It's got 3 massive planets with distances of about, the innermost ones are about 8 to 10 astronomical units from the star. I'm going to say something wrong now. Sorry, 20 astronomical units from the star, and 8 to 10 times the mass of Jupiter. And the star is also a scaled up version of the Sun. And indeed, there's some emerging evidence that more massive stars tend to form more massive planets, at least in the outer regions. Now, most of the exoplanets that have been discovered today have not been found by direct imaging, but through indirect methods. The most successful of which, at least initially, was the radio velocity method. So as the star and planet orbit their common center of mass, we can look for the motion of the star along the line of sight by monitoring its spectrum. So if we disperse the light from the star, we will see a spectrum with absorption lines, and these absorption lines will be Doppler shifted blue and red in alternance. And the first detection of an exoplanet that was widely accepted as a normal exoplanet by this method was in 1995, 51 Pegasus b. And what was surprising about this object, you can see here from the amplitude of the signal, which goes from about plus or minus 60 meters per second, you can deduce that the mass of the planet is of order half the mass of Jupiter. But the period, which is not shown here, is actually 3.5 days. So it's a very close-in gas giant planet. Many more of those have been found, and they're an entirely new class of planet known as hot Jupiters. They have very peculiar properties, in particular because they receive enormous amounts of irradiation from their host star, and they are thought to be tidally locked to the host star. So they have one extremely hot day side, very violent atmospheric dynamics, and very interesting atmospheric dynamics. From the radial velocity method, you get, from the radial velocity method, you get an estimate of the mass of the planet and its period and its separation from the host star. The other method, which has really come into its adulthood, so to speak, in the last 5 years or so, is the transit method. And I'm just going to go back to try and... OK. So as the planet passes in front of the star, if the orbit is aligned just right, then you will detect a small dip in brightness, which this simulation is for a star like the Sun hosting a planet like Jupiter. Then you will get a dip of about 1%. The depth of such a dip for an Earth-like planet in front of a Sun-like star is of order 0.01%, so 1 part in 10,000. Now, the transit gives you the size of the planet relative to the size of the star, and it also precisely gives you the inclination of the system, which is something you don't know when you have a radio velocity detection. And by combining the two, you get the true mass of the planet. Again, everything's relative to the star, but you get the mass of the planet and its radius, and from that you can estimate its density, mean density. The mean density gives you an idea of the bulk composition of the planet, and this is the first probe of the physics of the planet. Now, the first detection of a planetary transit was made in, well, it was made in 1999, published just 2000, using a very small telescope, which I'll show you in a minute, for a planet which was already known from radio velocity measurements. And again, it's one of these hot Jupiters, so the transit depth is a bit more than 1%. It's actually a little bit inflated. It's bigger than we'd expected. And it was made by a graduate student from a car park in Boulder using a 10 centimeter aperture telescope. That's one of the interesting things about transits, is that provided you can get the good observing conditions, you don't actually need enormous telescopes. You don't need high spatial resolution to observe them. However, the precision that you get here is just sufficient to detect transits of a giant planet. If you want to get transits of smaller planets, then you do need more sophisticated telescopes. So there are other methods which are becoming increasingly important. One of them is the astrometric method. So that's measuring the motion of the star on the plane of the sky as opposed to along the line of sight. And this little diagram shows the motion of the Sun caused by all 9 planets in the solar system, well, 8 planets. But most of the motion that you see is actually due to Jupiter. But I don't know if you can see the scale here, but the scale is relative to the radius of the Sun. So you can see that that motion is very, very tiny. And in order to see that for a distant star, you have to be able to measure its position extremely precisely with precisions of order 10 microarc seconds, which is what ESA's Gaia satellite will be able to do. So for stars within 200 parsecs of the Sun in about 5 years, we should be able to detect planets like Jupiter using this method. So massive planets on orbits of a few times the distance between the Sun and the Earth. And another method that I won't have time to go into in detail is the microlensing method, which uses the lensing of the light of a distant star by a low mass star in between. So if you have a distant star in the background acting as a source and a lens star passing in between, you get a microlensing event. So you get a brightening of the total light that you receive. And if the lens star has a companion, then you will get a small perturbation, which will reveal the presence of the companion. That is, if you can observe this with sufficiently high cadence. So that's the challenge with microlensing. It's actually potentially sensitive to some very interesting kinds of planets we can't find by other methods. So planets with masses similar to the Earth on orbits of 1 astronomical units and beyond. But the problem with this kind of measurement is that it's not repeatable, because of course once this star has moved on, you can't go back and look at it again. But so altogether, today we have many thousands of planets discovered, and this diagram shows them on a planet mass versus separation plane. So this is the separation in astronomical units and the mass in Jupiter masses, and each and every one of these points represents a detected planet, and different colors represent different methods. So the planets detected by direct imaging are generally massive planets far out from the host star. They're also typically planets around young stars, because planets glow brightest when they are young. The microlensing planets lie here at this intermediate distance range, and you can see they reach relatively low masses. Radio velocity planets are scattered over this kind of range, and then the transits follow a similar kind of range, but even more biased towards short period. Now, if I overplot the locations of a couple of the planets of the solar system, you can see that we are just starting to be able to detect some of the planets that are equivalent to those in our solar system. Many of the planets on this diagram have no equivalent in our solar system at all. The fact that there are no planets in these parts of the diagram, for example, doesn't mean they don't exist. It just means that we're not yet able to find them. The fact that there are, say, fewer planets in this region or in this region, however, that's not an artifact. So we are starting to be able to characterize the population of exoplanets and to say something about which kinds of exoplanets form around which kinds of stars with what frequency. There are, as I said, detection biases in this diagram. So, for example, the detection limit approximately of current radio velocity surveys lies around here. This limit here is due to the precision of the instruments, so the precision with which we can measure the motion of a star. This detection here actually corresponds to an orbit period of 20 or 30 years, and these surveys just haven't gone on for long enough to detect planets much beyond that. Now, I'm particularly interested in transiting planets, and that is because you can measure their masses and their radii and compare them to each other. And so this diagram shows for all the transiting planets that were known a few months ago and had good mass and radius measurements, the planetary mass, again, in Jupiter mass, and the planetary radius in Jupiter radii. Now here the mass is on a log scale, the radius is on a linear scale. So you can see we have radii ranging from more than 2 Jupiter radii. That should immediately throw alarm bells in your head. There should not be, it should not be possible to make a planet more than 2 Jupiter radii. But we'll discuss that a bit more. And down to radii similar to that of the Earth. And planetary masses also spanning this full range. Now, if I overplot a theoretical mass-radius relation for a pure ball of hydrogen and helium, that's in isolation, then basically this is the curve it follows. So stars lie along here, and real stars tightly follow this relation whilst they're on the main sequence. And then planets and brown dwarfs would follow this relation if they were purely made of hydrogen and helium in the usual ratios, and if there was nothing else going on. You can see that there's a lot more going on, and there's a number of points below the line, and it's easy to explain those by postulating that their compositions are actually a mixture of pure hydrogen and helium, but also potentially water vapor, rock, etc. You have to invoke significant fractions of iron and nickel in order to make planets more dense than this. To explain, so you have two main populations in this diagram. One of them is the hot Jupiters that we mentioned before, and then at smaller radii and masses we start to see the hot Neptunes and super Earths. And again, these are planets, I say they're hot because so far most of the transiting planets for which we have masses and radii have short orbital periods, and they have equilibrium temperatures of order 700 degrees Kelvin or more. You can also see there appears to be a gap, and this gap again appears to be real, and that must tell us something about the way in which these planets form. To explain the diversity of radii, particularly in the giant planet regime, the explanation most likely comes from the varying degrees of radiation, the varying amounts of radiation that these planets receive from their host star. So here I've color-coded the points according to the equilibrium temperature of the planet. So that's the temperature the planet would have if it was in radiative equilibrium with the radiation it receives from the host star. You can see the most inflated planets are those that are also the hottest. And nonetheless, we still don't understand quite why and how these planets are so inflated. As you go towards smaller planets, what you may notice is that the points are slightly smaller on average, and that is because the size of the points on this diagram represents the mass of the star, and it's easier to find smaller planets around smaller stars because they produce relatively bigger signals. Black points here just means we haven't got a good estimate of the temperature. So I'll just show two examples of how, for transiting planets, measuring the radius gave us some interesting clues as to its composition. And what kind of a planet it is. So Gliese 436b was the first hot Neptune to be discovered to transit. So it was a planet that was known from radio velocity measurements, so there was an estimate of its mass, although it was only a lower limit, and of its period. And people postulated that it might be an ocean world, primarily composed of water vapor and water ice, or it might be a rocky planet, and it would have quite different radii depending on which hypothesis was true. And then astronomers observed a transit of the planet, and the depth of it gave an estimate of its radius. This is a depth of only about 6 millimagnitudes, so 0.6%, quite a shallow depth. And the radius was found to be intermediate between those two, and actually requires a mixed composition with some rock, some water, some hydrogen and helium, or at least two of those 3 different components. And this is a problem we have for many of the smaller planets we try to characterize. Even when we measure their masses and radio, we still can't quite tell what they're made of. And we can't quite tell, therefore, whether there might be the kind of terrestrial planets that we think are most likely to be suitable abodes for life. In this particular case, it's also interesting to think about the physics of the water ice that probably is the primary constituent of a planet like this, because we're talking about very high pressure. So actually, in such a planet, most of the water ice is thought to be in the form of ice 7. And it would actually potentially have a liquid ocean on top of an ice layer. So quite a different world to what we're used to imagining. Now, to find smaller planets that transit, you can't do that from the ground, and you have to go to space. And there's been 2 missions, and one in particular in recent years, that have revolutionized this area by detecting thousands of exoplanets, called the Corona mission and the Kepler mission. And both of them are basically moderate-sized telescope. Corona was about 30 centimeters, Kepler's about 1 meter aperture, and they stared at large numbers of stars for a long time. And they looked for tiny little drops in the brightness of these stars that repeat. This is what data from one of these missions typically looks like. So this is a 5-month-long observation of a K star. And you can see these variations here. They're actually due to active regions that rotate in and out of view on the star. So the star rotates with a period of about 24 days here. And once you filter those out, you get this time series shown here in red. And in this time series, although you can't see it by eye, is a very definite transit signal with a period of only 20 hours. So although it's very shallow, it's a very clear detection because it repeats 192 times in the time series I showed you before. And this particular object is known as Corot 7b, and its radius is only twice the radius of the Earth. Its period is extremely short, as I said, less than a day. So it's thought to have a surface temperature of order 2,500 degrees Kelvin. And because of later mass measurements, we now know that its composition is probably primarily rocky. And because it's so close to its star, we think it must be tidally locked to it, so always show the same face. And therefore, objects like this, of which there's been a few more found recently, are thought to have a liquid magma ocean, potentially, on the day side. So they're very exotic objects again. Now, as I mentioned before, Kepler has revolutionized these fields. So all the points shown here with a black border are planets found by Kepler. And you can see that all of the lower mass planets in this diagram were basically found by Kepler. This is just an artist's impression of the first 1,400 or so planets found by Kepler. Here, every star and planet system are shown to scale. And this is the Sun with Jupiter for comparison. And you can see that there's a wide range of host stars. There's also a wide range of planetary radii. And there are, this is just a zoom, but there are a number of systems for which multiple planets have been found around the same star transiting. That if all the planets transit in one system, it means that they must all be in the same plane. And in fact, Kepler has revealed that small planets in close orbits tend to come in multiples. And so that means that they probably form via this process of forming in a disk, potentially migrating inwards under the action of a torque from the disk, but a relatively sedate process. When you find a larger planet near the star, typically you don't find any other small planets near the star. And that also tells us something interesting, that possibly the presence of a larger planet in the inner regions of a star disrupts the smaller planets in the system. Now, I'm going to spend a few minutes talking about what makes a planet habitable, because missions like Kepler were designed to measure the frequency of Earth-like planets or habitable planets, but we have to first define what we mean by habitability. And typically, there are 2 sets of criteria that are used to define habitable planets. One of them is a size criterion, and the other one is a temperature criterion. Now, it makes sense in the context of transit surveys to have a size criterion because we measure the size of the planet directly. So the thinking is that you don't want a planet that's too big because large massive planets they'll quickly accrete thick hydrogen helium envelopes. And so you have no surface, you have very large gravity, and that's not thought to be very conducive to the development of life. Although it just means it's not thought to be very conducive to the development of life as we understand it. it translates typically into mass constraints about less than 8 Earth masses, perhaps even a bit less than that. Radius constraints less than about 1.6 Earth radii. Now that number has a bit more of a firm basis in observation as well as theory. So basically that number has been derived by looking at the distribution of measured masses for the small planets that Kepler has found, and there appears to be a transition between predominantly rocky planets and planets with a significant hydrogen and helium envelope based on their density at around 1.5 to 1.6 Earth radii. We also don't want them to be too small. Low gravity makes it hard to retain an atmosphere, as Mars in our own solar system definitely shows. And it's also thought that plate tectonics and volcanism played an important role in the history of life on Earth, in particular in helping kick the Earth out of snowball episodes where you get basically runaway glaciation. And when runaway glaciation occurs, the only way to get out of it that we know of is by volcanism throwing up large amounts of CO2 in the atmosphere of the planet, and therefore starting an enhanced greenhouse effect that helps melt the ice, essentially. Now, as far as I know, there isn't really a firm lower limit on how small a planet can be and still be habitable. So far, it's been largely irrelevant because we couldn't, the smallest planets are hardest to find. But missions like Kepler are starting to find planets sometimes with Mercury sizes. So it is, it is an interesting question to ask. And as far as I know, it doesn't have a very clear answer. The other criterion, and the one that's most widely debated probably, is a temperature one. And that is a slightly less natural criterion to use observationally because we rarely directly measure the temperature of an exoplanet, certainly not its surface temperature. But essentially, the requirement is that the surface temperature should be such that liquid water can exist on the surface. And this leads to the concept of habitable zone. So there is a region in terms of orbital separation from the star in which the liquid water will be able to exist on the surface of the planet. And the inner boundary is essentially defined by runaway loss of the oceans, runaway evaporation of the oceans. And the outer boundary is actually defined by collapse of the atmosphere. The atmosphere just freezes out. And this habitable zone moves in as you go towards cooler stars because they emit less radiation. So that's the basic, simple concept of habitable zone. And it's natural to ask, why liquid water? Why is that such a widely used criterion? So you need some kind of liquid ocean, it's thought, as a solvent for chemical reactions to occur. And all life on Earth is carbon-based, and that's probably no coincidence. Carbon chemistry is rich and active at the kinds of temperatures that you find on Earth. Now, water is an excellent solvent for carbon-based molecules. It's possible to imagine other kinds of oceans that might support different kinds of life and that might be able to exist in other situations. And we should bear in mind that the criteria which might enable an ocean to survive on a planet are actually quite complex and quite finely tuned, potentially. And so on Earth, the carbon silicate cycle plays a very important role in regulating the climate of the Earth and whether or not it's able to develop and maintain a liquid ocean, even as the sun's radiative output has changed enormously in the last few billion years. Now, whether such processes occur that could regulate the presence of an ocean on different kinds of planets and with different kinds of oceans is an open question. So overall, the concept of habitable zone, you could argue, is flawed for many reasons. I've outlined the fact that water is not necessarily the only solvent you could use. We also just generally don't know what conditions are required for life, and we have only the one example on Earth to base our speculations on. It's very hard to evaluate the importance of the greenhouse effect on any given planet based only on the bulk parameters that we can measure, such as its mass and radius and its distance from the star. There are many other factors which will affect the climate, such as rotation rate, obliquity. The magnetic field of the planet will affect its ability to retain its atmosphere and to protect whatever is on the surface from damaging radiation. And the orbital stability of the planet is also a very important one. So if you have, for example, important oscillations in eccentricity, then you will destabilize the climate potentially. And so if you have planets interacting with each other in certain ways, it might favor or disfavor the orbital stability of the system. I haven't touched at all upon the possibility of there being other heat sources that might, for example, make a planet that would otherwise be too cold habitable. And I also haven't talked at all about the possibility of life below the surface. One of the reasons why this is not considered very interesting is because our chances of being able to detect it would be essentially none. At the moment, via remote sensing, we have no way of probing below the surface of an exoplanet. As I mentioned already, a star's luminosity changes a lot during its main sequence lifetime, so the habitable zone of a star is not a constant range, and you have to take that into account as well. But we have feedback processes that actually might mean that a given planet stays in the habitable zone for longer than you would naively think. And then you might also ask about whether it's wise to focus searches excessively on habitable planets. Because since we don't know exactly what a habitable planet is, by focusing excessively on a narrow definition of the habitable zone, we might be missing important things. So it's still useful as a concept to guide exoplanet detection and characterization experiments. We use it all the time in assessing, the extent to which a particular future instrument will be able to tell us something about life-hosting planets. But we should keep debating and questioning and extending the concept of habitability. And in fact, in recent years, people have shown that you can actually extend the habitable zone beyond. So the traditional habitable zone is what's shown in blue here, light blue. And people have shown that you can extend it if you have a very dry atmosphere. Basically, they can resist the runaway loss of their oceans at higher temperature. And if you have a planet which is further out from its star but contains significant amounts of molecular hydrogen, that's actually a very strong greenhouse gas. And so that can actually maintain surface temperatures such that liquid water can exist. I should also say that you might encounter from time to time something known as the empirical habitable zone, and that's basically just taking the range of orbital distances from Venus to Mars and scaling it to other stars. And that's been used as a way of saying, well, we should consider something slightly wider than what a restrictive calculation tells us. It's a bit of an arbitrary choice. Okay, so given these varying concepts of habitable zone, the Kepler mission has provided us with some estimates of the frequency of exoplanets in the habitable zone. So with the right range of orbital distances and of sizes. I'm sorry you can't read the axes, the projector is not very good. What this shows, each red dot here is a detection, a planet found by the Kepler spacecraft. These are planet sizes in Earth radii. And you can basically you have 1, 2, 3, 4, 5, etc. Earth radii. And then this is actually the stellar light intensity. So it's how much light the planet receives from the star compared to what the Earth receives. And there is a faint green box here, which represents what the authors of this particular study took to be their habitable zone. It ranges from 1 to 2 Earth radii and from a quarter of what the Earth receives to 4 times as much what the Earth receives. So it's a very broad box. And it actually lies exactly at the edge of what Kepler is able to detect. So in order to estimate the frequency of planets in this area, you have to apply a correction for the planets that Kepler could not detect. You also, of course, have to correct for the planets that don't transit, but that's relatively easy to do. And this particular study came up with a value of about 22%. So 22% of stars observed by Kepler host a planet in that region. You can scale it by changing the boundaries of this zone to get very different values. And then there are other studies that actually obtained completely different values, and the lowest value, actually there's another study which is not shown in this table, which used exactly the same parameters, but came up with a value of 2% simply by modeling the population in a different way and estimating the detection biases in a different way. So it's actually quite critical to bear in mind that we're using extrapolation to make this estimate still. But whether it's 2% or 22%, habitable planets, according to these very simple definitions, are not rare, right? Even 2% is a very large number when you count the number of stars. I had an aside here just to say that if you look at planets in this size and temperature range around M stars, they're actually extremely common. 50% or so of stars host one. And so you might think about whether an M-dwarf planet is habitable. A planet in the habitable zone around an M-dwarf will be easier to detect and easier to probe the atmosphere of. But the habitable zone is closer in for low-mass stars. And that means they're likely to be tidally locked and to receive a lot of high-energy radiation. And that opens a question about whether it might be a suitable place to look for life. So one way of looking for a habitable planet is if you can actually take a spectrum of the planet and look for atmospheric liquid water, that is a sure sign that there is an ocean. Because for temperate planets, for planets with reasonable temperatures, you should not expect large amounts of atmospheric water unless there is a liquid ocean to replenish it. So how do you take a spectrum of an exoplanet? Well, if the planet transits, you can do it via transmission spectroscopy, so looking at basically the apparent size of the planet at different wavelengths. When the planet goes behind the star, you can also get a spectrum. There you're looking at the emission and reflection of starlight. So this is a set of measured transmission spectra for hot Jupiters using data from the Hubble Space Telescope and the Spitzer Space Telescope, and it shows a continuum of cloudy to clear exoplanets that show more or less, this blue slope that you see in some of the planets is caused by clouds in their atmosphere. And these features in the infrared are mainly caused by water vapor in the atmospheres. Now, they're not habitable planets. More massive planets can retain atmospheric water without having liquid oceans. But the point is that we're able to say something about the composition of their atmospheres using this method. Unfortunately, we can even do it for smaller planets. So there's a super-Earth, Gliese 1214, for which we have measured transmission spectra. For super-Earths, it can actually be a way of distinguishing between a puffy atmosphere mainly made of hydrogen and a denser atmosphere, say, mainly made of water. In this case, the spectrum is very flat, which might suggest that it's got a thinner, denser atmosphere, but in fact it's been measured to be so flat that we now know it must be cloudy. It's not just that it's made of water. I'm skipping ahead a bit because I want to get to some of the rest. So you can also measure the thermal emission spectra of hot Jupiters when the planet goes behind the star, and that gives you again an estimate of the composition and the atmospheric temperature of the planet. And so this is an example of a thermal emission spectrum of a star. This is the transmission spectrum for the same planet, and this is its thermal emission spectrum. And in both cases, what you see is an absorption band of water vapor. But if you want to do this for a planet like the Earth, the atmosphere is too thin for transmission spectroscopy, and the contrast is too large for secondary eclipse spectroscopy. So you have to directly resolve the planet. And there are a number of experiments on the world's largest telescopes today that do this essentially by trying to block the starlight using a coronagraph, as well as trying to correct for the distortions of the images that the atmosphere of our own Earth imparts on the images. And so, for example, the same system I showed you at the beginning, we can now observe with much greater detail by placing a coronagraph, blocking the starlight, and having better image quality. And you can see that's revealed an additional planet even closer to the star. And what's nice is once you separate the starlight, you can actually take a spectrum. So you can disperse the light of the planet and take a spectrum of it. And in this case, you can look for expected molecules in the atmospheres of these planets. These planets don't have methane in them. We're expected to have methane in them. That's interesting. I'm going to skip over. This is another similar instrument on the Very Large Space Telescope. Very Large Telescope, sorry. It's been used to detect a debris disk around a binary star. That's a very interesting thing as well. In the future, the European Extremely Large Telescope, which is a 40-meter telescope that will see first light sometime in 2018, 2020, ultimately will have an instrument dedicated to direct imaging as well that may be able to find Earth-like planets around low-mass stars. But if you want to do it for an Earth-like planet around a Sun-like star, this shows the contrast that you have to achieve as a function of separation. And to do it, you need to reach contrast down to 10 to the minus 10 at separations of as little as 0.1 arcsecond, or even smaller if you place the system further away. And to do that, you have to go to space. And so there have been a number of concepts that have been proposed for large space telescopes. These would actually be fantastic machines for other aspects of astronomy as well. But if we equip them with a state-of-the-art coronagraph, then we can survey large numbers of stars. I'm going to skip this, but it's an interesting question about how many planets do you need to characterize in order to measure the fraction that hosts life if you don't know in advance what that fraction is. It drives the requirement for the size of that telescope. This is a simulation of what such a telescope might be able to see if you place the solar system at 13.5 parsecs away. And this is a simulation of the kinds of spectra you might be able to see. Now, we are looking for biosignatures, molecules that are traces of biological activity. And unfortunately, I think I'm running out of time, which is a shame. What I wanted to say, you can look for them in the optical or in the infrared, but what I wanted to say really is what kinds of things we can look for. And there are basically, typically, there are 3 types of biosignatures. One of them is simply when you have geophysical processes that create a chemical potential energy gradient, and there's a reaction which would release energy, but there's a potential barrier. Life exploits that by acting as a catalyst. And examples of molecules that are produced by such a process on Earth are methane, nitrous oxide, sulfur dioxide, hydrogen sulfide. And these are abundant, but they're produced by other things as well than life. So they're not very useful as biosignatures on their own. The other type, which is the most popular, is the O2, and it's part of a class of biosignatures that are the byproducts of biomass building. If you really want to think about all possible biosignatures, you have to consider all small molecules abundant on a planet like the Earth, all the reactions and all the products that they can yield, and then which of these are not produced by any geochemical process, and which of these are going to be abundant enough. Because there are also molecules that are produced on Earth only by life, but they are in such small amounts that we could never detect them from space. So O2 is at the moment the canonical biosignature gas. It's highly reactive. It has a short atmospheric lifetime. So without active photosynthesis, there would be none or very little in the Earth's atmosphere. Now, the present level, it's important to realize, is the result of a balance. And it has changed in the past due to competing effects. So I just finished to say there is no single no-brainer biosignature, and the most important thing is to aim for wide wavelength coverage, because if you find one molecule that suggests you have life, you will need to look at the rest of the composition of your atmospheres to understand if it really is produced by life. And I'll leave it at that.